Section 6 really has two purposes. One purpose is to show us, if you will, the basic graph for a number of functions in its simplest form. All other graphs that are similar to these graphs are simply moved around or perhaps squeezed or stretched out, but they'll all have the same basic form. The other part of this section is to introduce you to the idea of continuous or discontinuous. Something is continuous when basically if you were doing a hand-drawn graph, you could draw the entire thing without lifting your pencil from the paper. On the other hand, discontinuous is when it's broken, in which the graph actually has a break in it, a gap, if you will. Now, the basic graphs we have, let's go ahead and zoom in on this so we can see them a little bit better. So first, the most basic straight line, it goes through the origin, so there's no, shall we say, extra part, y-intercept part. It's just f of x equals x. The slope is 1. So every x value and y value is the same. It's just a diagonal line at 45 degrees through your graph. A squared function, f of x equals x squared, will give you the parabola and its symmetry. Notice, again, these are all going to go through the origin 0, 0, but in this case, the vertex is at 0, 0, and then notice the 1, 1, the 4, 4, the symmetry of the y values. And so whatever is the left side and the right side will match. That is an example of a quadratic or a squared function. Here is our cubed function. Basically looks like an S or a snake kind of shape. And the key here is because cube grows so quickly, we only tend to do just a few points. The numbers 0, 1, and 2 for the x's, whether positive or negative, because that already gets us to 8. If we were to go to 3, 3 cubed is 27. That might already be bigger than the graph we want to make. We introduced the square root function earlier in the chapter. And again, the key is find your squares so that when you take the square root, you'll have whole numbers to graph. On the other hand, here is a cube root function, which looks very similar to the cube function, except it's been rotated on its side. Absolute value function gives us our v. So u for the squared function, v for the absolute value function. Now, all those are things that we have seen before. The chapter then introduces two new functions. One is called the greatest integer function, in which basically you round all the points that are in between the whole numbers up to a whole number, and then it has gaps. So notice the jumps. This is also called a step function. You can kind of see the way it makes a staircase as it's going up. But if you look at the x and y values, you can see how they've been rounded to a whole number. And then the last example it shows us for functions is what's called a piecewise function, where literally the function that you're using to make the graph changes at some point, as long as it's continuous. Note that, in fact, both of these functions will give us the exact same value at 0. Here we'll have 2 times 0 plus 3, so we have 3 at 0. Here, put in 0, we'll have 0 plus 3, so again we'll have 3 at 0. So this is continuous all the way through, but clearly the type of function that we're using changed at 0. The last example that they gave us for a graph, notice they did not use the word function, they used relation. And the relation here is because, of course, this is a parabola on its side. Notice that it's the y part that's squared, not the x part that's squared. So if we go back real quick to the top, that was f of x equals x squared that gave us our up or down parabola. Well, here it's on its side because it's the y part that's squared. But it's not a function because, of course, if I used a vertical line test through it, it would hit it more than once. It is not a function. All right, so that's basically what the section is about. And now we're just going to do some example graphs. So in this first case, we're going to look at a piecewise function. And, one of the things that you could do is just make a series of t-charts. Make some t-charts here for values to graph over the different intervals. And in this particular case, I know that they're all straight lines because the x's don't have any exponent to them, so these are all straight lines. So I need simply to do the beginning and the end points. So I'm going to start off with 4.5 times 0. Give me 0. 4.5 times 4 will give me 18. So for the top function, I'm going to go from 0 up to 18. So I'm going to start here at 0, 0. And then at 4, I'm going to go up to 1, 2, 3, 18. So that's the first part that I have graphed. But that's just 0 to 4. Okay, in the next one, plug in 4. 4 times negative 6.5 is negative 28, negative 28. No, negative 26, excuse me. Negative 26 plus 44, it turns out it's also 18. So it's going to give me that same point there. I plug in 6. Negative 6.5 times 6 is negative 39. Negative 39 and 44 gives me a 5. So it's 6. I'm going to drop all the way down to 5. The next one. So right there. And the last one starts at 6. Again, plugging in 6. 6 times negative 30 is negative 180. Negative 180 plus 185 is again 5. So we will be continuous. And then at 6 and a 6, it turns out plugging in 6 and a 6 gives us negative 185 plus 185. And so we're back to 0. Now, 1/6 is not very far past 6. So I'm just going to approximate it right there, just so that I can see that the slope has changed. And there is an example of graphing a piecewise function. All right, now we're going to look at an example of a step function. Now, in this particular case, just to kind of give me some room, you can make your vertical and horizontal axes anything you want. So I'm going to, since it's already been printed, I'm just going to make these all over 4. So in a horizontal sense, every line is 1/4. And then I'm going to start off with making a t-chart. Again, anytime it's a function that's a little bit odd, I can make a t-chart. So if I start with 0, 1 minus 0 is 1. Step function is not going to change that. I'll still have a 1. If I put in a 1/2, 1/2 times 2 is 1. 1 minus 1 gives me 0. Put in a 1, end up with -1. 1 minus 2. If I put in a 3/2, I'm going to have 1 minus 3, which is -2. And if I put in a 2, it's 1 minus 4, so it's -3. Let's go in the other direction. What if I put in a -1/2? Well, that'll be 1 plus 1, which is 2. And then I'm going to put in a -1. So 1 plus 2, that's 3. And -3/2 will give me a 4. So at 0, I'm at 1. So that means basically I'm going to be right here. And then since every line is a quarter, and I was going by halves here, I can go 2 lines at a time. So this part here, I'm going to make an open circle. In other words, that's a not equal to. And so my first little segment is going to be right there. Now, once I get to a half, I'm at 0. So the next one's going to come down here. And then it's also going to go over to there. That's an open circle again. And then I can, of course, continue on. Now I'm going to be down one more line. Close circle there, open circle there. And of course I can go back the other way. And so here's an example of graphing the greatest integer function, which is also called a step function. And I simply changed the horizontal axis so that I could actually see what I was trying to graph. You can make it anything you want, and that's one of the things to consider when you're doing a graph is I want to make the interval between lines big enough or small enough, depending on the situation, so that I can see the whole graph. All right, now we have a word problem that is an example of a problem that is a piecewise. So we have a person who drove at 50 miles an hour to a friend who was 180 miles away. They stayed for 4 hours, and then they returned at a faster rate of 60 miles per hour. And we want to sketch a graph of that. So let's do, again, some T-charts. T-charts make things easy, and I'm going to do 3 of them because there's 3 different intervals, if you will, for this person's travel. Now, of course, they started out at 0 time and 0 distance. They've gone. Now, after 3 hours, they've gone 150 miles. To go 180 miles will take 3.6 hours. Now, once they get there, they don't move. So I'm going to start off 3.6. They're still at that 180. But then at 4.6, they're still at 180. And 4 hours later, so that's at 7.6, they're still at 180 because they didn't move. And then they start back. So at 7.6 again, they're still at the 180. But now they're going at 60 miles per hour. So at 8.6, they're now at 120. 1 hour, they've gone 60 miles. And it'll take 2 more hours to get all the way home. So 10.6, I'll be back where I started. Now, in terms of the graph, one change I'm going to make is, again, they're already printed, but I'm going to just say that's 50 miles, that's 100 miles, and that's 150 miles away. So we started off with, we were at home. At 3 hours later, we were at 150. At 3.6, we were at 180. So approximately up there. Okay, then we stayed there for 4 hours. So 1, 2, 3, so approximately right in there. These lines are close enough together. I'm not really going to worry about whether it's 0.5 or 0.6. It's close enough on my graph. And then at 10.6, I have to be back home. And so my graph should look like this as a graph of my journey. And so there is number 3. A little bit of different slope, 50 miles per hour versus the 60 miles per hour coming. All right, problem 4, our last example, will give you a real-life example of a stepwise type function. It says the cost of parking a car at a parking lot is $5 for the first hour and $2 for each additional half hour or fraction of a half hour. Graph the function f that models the cost of parking a car for x hours over the interval from 0 to 4. All right, so and I'm just using x and y because I'm doing a graph. So right off the bat, it costs $5 to get in. Now, it's $2 for each additional half hour or fraction thereof. So for the first hour, it's going to cost, because again, to get in there, that's the $5. Okay, so past 1 half hour, now I incur the next $2. And then the next half hour, up to that next half hour, I'm going to have $2 more. And so I'm just going to keep going by halves. And then an extra $2 each time. And then up to 4. So it'll be 19 at that point. So it'll start off with 0 and 5. Now in this particular case, I'm going to make every line be a half. Again, just to make it a little bit easier using the paper I've already got. So every line's a half. All right, so at 1, I'm going to jump up to 7. But up until that point, so 5, 6, 7, up until that point, it's just the $5. And then it's going to jump 2. Now I'm up at 7. And then it's only going to go a half an hour. And then it's going to jump. And then a half hour. And then it's going to jump. And so forth. So let's see. Oh wait, I got to jump 2. I only jumped 1. Sorry about that. So jump 2 will put me up here. I accidentally only jumped 1. I needed to jump 2. And then I need to jump 2 again up to 11. So that will put it here. and then this one will be open, and then 2 again, and then open, and then 2, and then open, and 2, and then open. So basically, my graph, sorry about the mess up, but where are my steps? Now, if I'd used 4 like I had above, instead of divide by 2, then I could have made each of those little stair steps twice as wide. But this is the idea for how a staircase would work. And so that is section 6.